Hello, and this time we're looking at differential equations and ones which can be solved using an integrating factor. Now we'll just dive straight into the examples. I think that's easier. And here we've got x cubed y by dx and 3x squared y and equals sine x, but we won't worry about the sine x for now. It's this that's interesting. X cubed and 3x squared, well, they look sort of linked. X cubed differentiated is 3x squared, and of course y differentiated is to y by dx. What we've got here is the product rule for differentiation, which, if you can't remember, says that if you have a function of x times another function of x and you want to differentiate this, then what you get is the first function times the differential of the second plus the second function times the differential of the first. So make that differential. Okay, and so if we think about this as x cubed and y, let's just check it works. D of x cubed y dx would be the first, x cubed, times the differential of the second, dy by dx, plus the second, which is a y, times the differential of the first, which is 3x squared. And that is exactly what we have here. Okay, exactly what we've got. So we can just rewrite this thing as this differential here. And so I can just delete all of this and say, well, if this is the same as this, and this equals sine x, then we can just say this equals sine x there. And now we can solve it by integrating both sides. If we integrate this side, we're just going to get x cubed y. And if we integrate this side, we're going to get minus cos x plus c. And you could rearrange this, get rid of the x cubed by dividing to get y equals if you needed that. But I'm going to stop there as we've got the integration. Anything else is just rearranging it to the form that the question's asking for. Okay, so let's have a look at this question. Now, this was delightful, this first one, because it happened to be that we could use this product rule. This one is not going to work in the same way because we haven't got something on the front of the dy by dx that we can then say, oh, well, this is a product rule. But it would be good if we could make it into the product rule. And we can do that like this. Dy by dx plus p to the x y equals q to the x. If that's what we've got, dy by dx is plus a function of x times y equals a different function of x. And what we're going to do is times every term by e to the power of the integral of p to the x dx. And if we do that, it should put us into this situation where we can do a product rule. We can reverse product rule to simplify the situation. So let's have a look at that applied to this guy. And the p to the x here, I don't really care what the other side is. It could become something quite difficult to integrate, I suppose. But for the moment, we're not interested in that part. It's sort of setting up the left-hand side. So the p of x, the function of x we're looking at, is 2x. So if we write this out, well, no, let's work out this bit first. So e to the power of the integral of 2x. Well, the integral of 2x is going to be x squared. So we're going to times everything in this equation by e to the x squared. And we get e to the x squared dy by dx plus 2xy e to the x squared equals, and then if we times e to the minus x squared by e to the x squared, we're just going to get 1. And now we need to check if this is the product rule. So I'm going to get rid of this side so we've got a bit more space to work this through. If this is a product rule, then e to the x squared and y seem to be the two things that we're doing. So the differential of e to the x squared y dx would be the first, e to the x squared times the differential of the second, which is good, that's what we've got, plus the second times the differential of the first. and differentiating e to the x squared, you're going to get e to the x squared, and then times the differential of x squared, which is 2x, and that's the same as we've got here, 2xy e to the x squared, 2xy e to the x squared. So we can write it in this simplified form of d of e to the x squared y dx equals 1. And we can integrate both sides, and we just get that e to the x squared y equals x plus c. And again, you can rearrange that now. If you need it in y equals, then just divide both sides by e to the x squared. So hopefully you can see that if we use that, that trick, here's a couple more examples. I'm just going to write that trick out again, that if you have got dy by dx plus p of x y equals q of x, then you times every term, you multiply by e to the power of the integral of p to the x dx. And it should turn into that reverse product rule situation. So let's have a look at these two examples and see what's going on. Okay, so in this case, it looks quite straightforward. It is dy by dx plus something times y equals some function of x. It doesn't have an x in, but that's okay. The function of x, p of x, is just 2. It doesn't have an x in, but that's okay. So we're going to times everything by e to the integral of 2 dx, which is just going to give us e to the 2x. So we're going to say e to the 2x dy by dx plus 2y e to the 2x equals, and then we've got to times this by it as well, so it's e to the 3x. And we should be able to write this with the product rule, so let's just check that it works. So d of e to the 2x y dx, I think it's good to just check it like this rather than assuming. Then what we're going to get, we're going to have the first e to the 2x times the differential of the second, dy by dx, so that's good, plus the second y times the differential of the first, which is e to the 2x times 2, so 2y e to the 2x, 2y e to the 2x, so it does work. So we can replace this side with d of e to the 2xy by dx, and integrate, and we're going to get that e to the 2xy equals, the integral of this is going to be 1/3 e to the 3x plus c. And again, you can just divide both sides by e to the 2x to get your y equals. Okay, so this is really handy. If you see it's in this form, then it's a nice little trick to get it to work through. We'll just rub this out, just do the last example. I imagine we'll need lots of space for this one. Okay, now it looks good, doesn't it? Because we've got dy by dx and y, and we've got sine and cos, and they differentiate to each other. So it looks like it's like that first example where it's already set up in this completing the square. So let's see if that works. D of cos xy dx. What would that be? Well, it will be the first cos x times the differential of the second, dy by dx, plus the second times the differential of the first. But the differential of the first would give us minus sine x, and that would equal 1. And that's not the same as we've got. We've got plus here, not minus. So this is an issue. So we need a new strategy for this one. And what we're going to do is we're going to turn it into what we have here, this little trick of dy by dx, a function of xy, and a function of x on the other side. And we're going to do that by dividing by cos. So we're going to get dy by dx, because the cos is divided away, plus sine divided by cos is tan. So it's y tan x, and this equals 1 divided by cos, which is sec x. Now this looks like the form that we've been working with, so we can times everything by e to the integral of p of x dx. So what is that? So e to the power of the integral of tan x dx. And the integral of tan x is log of sec x, and the e and the log are going to cancel and just give us sec x. So now let's multiply everything through by the sec x, and we're going to get sec x dy by dx plus y tan x sec x equals sec squared x. And let's just check that this works. So if we get rid of this side, and so this should be d by dx of y sec x. I'll put the y first so you don't think that it's inside the sec. So this would be the first times the differential of the second, so that's fine, plus the second times the differential of the first. And the differential of sec x is tan x sec x. So it is giving us exactly what we need. So that's good, so it's working. So we can get rid of all that then. That was just to check that we were on the right lines. And we can rewrite this now as d of y sec x dx equals sec squared x. And we can integrate both sides. So on the left we're going to get y sec x, and this equals the integral of sec squared, which is tan x plus c. And of course you can get rid of the sec by dividing, and if you wanted it as y equals. But hopefully you can see the little method here of getting into the form of dy by dx plus a function of x times y equals a different function of x, timesing by the integral of this function of x, the one in front of the y. That will put it into a form that you can then do reverse product rule, and then it's just a case of integrating both sides. So if you've got a differential equation and you can get it into this form, then hopefully now you have an idea of how you can solve it. Any questions or comments down below? Otherwise, cheerio.